Hello friends, Shivansh this side, and today I am going to show you the simplest derivation of Schrodinger equation. And first of all, let me tell you what Schrodinger equations tells me. It is the most basic equation of quantum mechanics and tells us the energy which waves consist. I will tell you with the mass one, like which is independent of time and dependent on mass. So let's start with it. Before starting, first of all, I would like to say please subscribe my channel, please like my video, and please share it to as many people as possible. And you might have seen my video make your own trigonometric identity, in which I told you that e raised to the power ix is cos x plus I of sin x. So here, let's start with it. Actually, I told you for that video because in this thing in psi is equal to e raised to the power ix plus omega t, we would be using it. But before that, let's start. First of all, quantum mechanics deals with the particles which can be represented as wave 2. So if this is a wave, then okay, I thought where my pi has gone. So this is wavelength. Okay, this is wavelength, and k is 2 pi upon lambda is wave number. We say it as wave number. And what we know about frequency? Frequency is simply number of number of wavelength, like what I say, number of number of waves occurred in a second. Like actually I stumbled. So this is known as angular frequency, this is known as wave number, and something below it is Planck's constant. It is reduced Planck constant, h upon 2 pi. It is wave function, as I told you, and I is square root of -1. So before starting, main thing is that why I took it as wave function, or why most mathematicians, I like think all mathematicians and physicists take it as wave function, because e raised to the power ix is cos x plus I of sin x, and wave function is combination of sine function as well as cos function. So that's why to integrate both the functions in a appropriate way, we take this as wave function. So after this pretext, let's start with our derivation. So before starting, let's use a simplest equation of classical mechanics, which is T, let it be total energy. T dot, okay, I would represent, is represented by T only, is K plus V. Here T is total energy, K is kinetic energy, and V is potential energy. Okay, we are going to work on kinetic energy. So there is something known as Hamiltonian operator and etc etc. But I am telling you most basic thing. The most basic thing. So let's obtain it for, sorry, actually upon the hyperlink thing. Let's obtain it for kinetic energy. We know that kinetic energy is half of mv square. Okay, so half mv square is kinetic energy, and we also know that m into v is momentum, linear momentum, and mv you might